All right, welcome back to even and odd functions. Oh, I think I should be using my glasses now. You know, we know we have heard about even and odd functions, but what are these even and odd functions? How are they related to Fourier series? So we want to see how even and odd functions are actually related to Fourier series. But before we start seeing how they are related to Fourier series, I would like us to know what even and odd functions are. Now, let's say we have a function f of x, and then if we should substitute a negative value for x, if we should get our function back, it means the function is even. But if we should have the negative of that function, it means the function is odd. So in even and odd functions, I would like us to see them like algebraically. That is, we are going to do some operation on how they work algebraically. And also, I would like to evaluate them or see them graphically, how even functions are when you graph them. So, because if we know how even functions are when you graph them and algebraically, finding Fourier series will be very, very easy. Like when I mean easy, it will be very, very easy. Because once we know how they are, there are some coefficients we don't need to find if the functions are even or odd. So let's get started. Let's see even and odd function algebraically. So if I have a function f of x and I take the negative of that function, if I get the function back, then the function is even. What that means is that if I have a function say f, and of course if I take the negative of that function minus x, and if this gives me the function x, then we can conclude that this function is even. They are very easy to know. But what if I take the negative of the function and then I obtain minus f of x? Then you can conclude that this function is odd. So that's just it about even and odd function algebraically. If you should take the negative of the function and you obtain the function, then the function is even. If you should take the negative of the function and you obtain minus of the function, then the function is odd. What if you take the negative of the function and you did not get neither the function nor the negative of the function? Then the function is neither odd nor even. But we are going to see that. Let's take an example. Example. Now, suppose we have f of x equal to 2x squared plus, let's say we have 2x squared plus 4. This is the function 2x squared plus 4. We want to verify if this function is even nor odd. Now, we are asked that if we take the negative of the function, we are going to get the function, then the function is even. Let's go ahead and substitute minus x for x. So we are going to have f of minus x, and this is equal to 2 into, in place of x, we substitute minus x to the power of 2 plus 4. And this will give us, because 2 is an even number, minus x raised to the power of an even number will give us x squared. So we have 2x squared plus 4. So this means that this function is even. So we have that the function is even. Take another example. If we have f of x equal to, let's say, 3x cubed plus x. 3x cubed plus x. And let's check if this function is even or odd. So we have to substitute x for minus x. So we have f of minus x is equal to 3 into minus x to the power of 3 plus minus x. And this will give us minus x to the power of 3 will give us minus x cubed, because 3 is an even odd number. It's just like saying minus x times minus x times minus x. Minus x times minus x will give us x squared. X squared times minus x will give us minus x cubed. So that is what we have. So it means we are going to have minus x cubed here. So this we have minus x cubed minus times 3 will give us minus 3x cubed and then minus x. But minus is common, so we can factor out minus. So we are going to have minus into 3x cubed plus x. So you see that we take the negative of the function, we take x to be negative and we obtain negative of the function, negative of the function itself. So it means that this function is odd. So let's take another example to illustrate even and odd function. Suppose we have f of x equal to, let's say, 4x to the power of 4 plus 3x squared um, plus 5. Let's say f of minus x will be equal to 4 into minus x to the power of 4 plus 3 into minus x to the power of 2 plus 5. And of course, this will give us 4 minus x to the power of 4 will give us x to the power of 4. X to the power of 4 minus x to the power of 2 will give us x to the power of 2 plus 3x to the power of 2 plus 5. So therefore, f of x equal to 4x to the power of 4 plus 3x to the power of 2 plus 5 is even. All right, so let's take another example. The fourth example there is if we have f of x equal to, let's say, 3x cubed plus 4x squared plus 6x plus 5. It means that f of minus x will be equal to 3 into minus x to the power of 3 plus 4 into minus x to the power of 2 plus 6 into minus x plus 5. So we are going to have minus 3x to the power of 3 plus 4x squared minus 6x plus 5. Now, if you should observe carefully, if you should observe carefully, you see that we can't even factorize minus here. And the function is not in this form. The function is not in this form. And it's not also in this form. Because we cannot factor out minus here to have minus f of x here. And also, the function is not f of x itself. So it means that this function is neither odd nor even. So the function is neither odd nor even. So please take note. In case you have any Fourier series question, if the function is neither odd nor even, just go ahead and find everything. So this is what we have for even and odd function algebraically. Let's see how they are graphically if you should graph even and odd function. So let's see them graphically. So we have this. I will take the first, like, two examples for even functions and two examples for odd functions. So the first one there is, if we have this, we have this. Let's assume we have something like this here, going this way. Just going like that. And we have another here, going like that. Just like that. Now, if you observe, If you observe, what I have here is what I have here. Yes, and what I have here is also what I have here. It means what I have here, I'm going to have it here if I should continue this. So it means that if you observe carefully, you see that, because if you observe, you see that this is symmetric about the y-axis. It is symmetric about the y-axis. So please, graphically, for even function, the graph is symmetric about the y-axis. And for odd function, the graph is symmetric about the origin. But don't worry, we are going to see for odd function. But for even function, if you should see, they are symmetric about the y-axis. What I have here is what I have here. What I have downward here is also what I have here. So this function is even. So this is an even function. Where should I even write it? This is even. Even function. It's an even function. Now the second example there is what if we have something of this nature? We have something like this. And of course, this can continue this way. This will continue this way. Observe this carefully. Is this not a cosine graph? This is a cosine graph. This is a cosine graph. And you see, what I have here is what I have here. What I have here is what I'll be having here. So it means that this function is an even function. And it don't mean that cos is an even function. So it means that if cos is an even function, if we should take the negative of cos, we are still going to get the function itself, because we have seen here that the cos graph, the cosine graph, is an even function. So take note, these two are even functions graphically. So let's see for odd functions. Let's see how odd functions are. Okay. We have, suppose we have this, and let's say when x is equal to 1, y is 1. When x is equal to 2, y is 2. When x is equal to 3, y is 3. If you plot that, you are going to have something of this nature. It will pass through the origin, and this is a odd function because we say it is symmetric about the origin, what you have here. So if you observe this carefully, we have two the same shape in two successive quadrants. So it means this is an even function. What we have here is what we have here, two successive quadrants. And also, if you observe for the odd function, we have in the first and third quadrant. So it means that if we have another function of this form, this is also odd function. It's also odd. They are opposite, first and third, second and fourth. You see? So this is for odd function. What if we have another of this form? We have something of this form. And this will continue. And we also have, perhaps we have something like this. Is this not a sine function? This is a sine function. F of x equal to sine x. And this is f of x equal to cos x. If you should observe, what I have here is what I have. This and this, they are opposites. I also have this and this opposite. I have this and this opposite. So I'm going to have another here opposite. So it means this function is odd because they are symmetric about the origin. So this is a odd function. So if you have any function of this form, they are odd. And if you should have any function of this form, they are even. So in case you are asked to find any Fourier series, and perhaps if you plot the graph, you have something like this. Don't find, there are some coefficients you don't need to find, but just take note of these even and odd functions graphically. Because it's not all time that this algebraic method will work for you. You need to check them graphically also. So this is for even and odd function. So this is odd. and this is also odd. So this is what we have for even and odd functions. Um, Fourier series for um, even functions. Fourier series for even functions. All right. Now we have that for Fourier series we have f of x equal to a naught over 2 plus the sum as n equal to 1 to infinity of a sub n cos nx. But what we are interested is the Fourier coefficient. So the first one we have there is a naught equal to 1 over pi. Don't forget, please check the video for this. 1 over pi, the integral from minus pi to pi of f of x dx. So this is what we have. Now, we are talking about Fourier series for even functions. Fourier series for even functions. It means that Fourier series for even function, it means that f of x, which is the function, is even. It means f of x is even. That is what it means. Fourier series for even functions. F of x is even. So if f of x is even, let's come back to this graph here. Let's come back to this graph. Let's come back to this graph. Or should I use okay, let's use this. Let's use this. Now, if this is the function, the even function, assuming, okay, I would like to draw this again. This is what we have. Let's say we have here to be minus pi. Of course, this is minus pi, and we have here to be pi. And let's assume we have something of this nature, and we have another. Please, maybe because of how I drew the graph, here and here are actually equal, please. They are equal. These two are equal. This is pi, and this is 0. Now, if the area under this curve, is A, it means the area under this curve will also be A, because they are equal. Now, we want to integrate this function from minus pi to pi to find the area of this function. Now we see that, okay, instead of integrating this function from minus pi to pi, why can't we just integrate this function from 0 to pi and then double the result? Because we see that from minus pi to 0 and from 0 to pi, they are the same thing. From minus pi to 0 is A. From 0 to pi is still A. So why can't we just integrate from 0 to pi and then double our result, since the function is even? So that's what it means. So it means that instead of integrating from minus pi to pi, because the function is even, we can just integrate from, this is 1 over pi, integrate from 0 to pi, or from minus pi to 0, from 0 to pi, of f of x dx, and then double our result, 2. That's what it means, 2. Instead of integrating from minus pi to pi, we just integrate from 0 to pi and double the results, since what we have here is what we have here. So it means that the Fourier series for even functions, for a naught, we have this. What of a sub n? A sub n is equal to 1 over pi, the integral from minus pi to pi of f of x cos nx dx, of f of x cos nx dx. Now, we said Fourier series for even functions. It means f of x is even. f of x is even. This is what it means. But cos is also an even function. From the graphical method for analyzing even function, we have seen that cos is an even function. So it means that cos here also is even. Cos is even. And even times even will give us even. Please take note. Even times even will give us even. It's just like saying, what do we mean by even times even will give us even? Let's see. Assuming we have assuming we have x cubed, x cubed, x squared, sorry. X squared is even. If you should multiply by another even function, say x to the power of 4, 4 plus 2 will give us 6, which is x to the power of 6. So it's still even. What about if we have odd and we should multiply it with, let's say, even x to the power of 4? You see, we are going to have x to the power of 7, which is odd. So what does this imply? This implies that even times even will give us even. Even times odd will give us odd. What about odd times odd? If we should have x to the power of 3 times x to the power of 7, and this will give us x to the power of 10, which is even. So please take note of these three conditions. Take note of these three conditions. Even times even will give us even. Even times odd will give us odd. Then odd times odd will give us even. Please take note of these three conditions because it will be very important for us in Fourier series. So we have that f of x is even from the Fourier series for even functions, and cos nx is also even. So even times even give us even. So if even times even give us even, it means instead of integrating from minus pi to pi, we can integrate from 0 to pi and double the result, because we have seen that for even functions, we can actually go from 0 to pi and double the result. So it means that a sub n will be equal to 2 over pi, the integral from 0 to pi of f of x cos nx dx. So this will be the new formula for a sub n and a naught for Fourier series of even function. What about b sub n? Remember the three coefficients we have are a naught, a sub n, and b sub n. What of b sub n? B sub n is equal to 1 over pi, the integral from minus pi to pi of f of x sine nx dx. Now we are talking about Fourier series for even functions. It means f of x is even. So we have even here. And we have sine nx. Sine nx. We see from the sine graph that sine is the odd function. Sine is actually odd. So it means we have odd here. Odd. And even times odd will give us odd. Don't forget. Even function times odd function will give us odd. So it means that this function, the whole of this function will become odd. So we can't use this or this again. So we have to use this. And for odd function, we have this. Don't forget. For odd function, we have this. Instead of having this shape here and here, I'm going to have one here and have one here. So it means I have this. And I also have this. So if you observe carefully, the area under this curve is equal to the area here. But they are opposite. If the area is A here, here will be minus A. They are opposite. Opposite. So if here should be minus pi and here is pi, if I'm to integrate from, and here is 0, the origin is 0. If I'm to integrate from minus pi to pi, it means that I can integrate from 0 to pi and then double the result. Because if you see, we integrate from 0 to pi and then double it, a plus a, give us 2a. So it means if we want to find the area here, we need to integrate from 0 to pi and double the result. That is from 0 to pi and minus a plus a, which will give us 0. Minus a plus a, and this will give us 0. So it means that b sub n it means that b sub n is equal to, because 0 times the whole of this will give us 0, b sub n is equal to 0 if the function is even. So that's it. So please take note, for Fourier series for even function, a naught is equal to 2 over pi the integral of f of x dx. A sub n is 2 over pi the integral from 0 to pi f of x cos nx. And b sub n is equal to 0 for even function. Now let's find Fourier series for odd functions. Fourier series for odd function. Fourier series for odd functions. For odd functions. Let's see what we are going to have. Fourier series for odd functions. Oh, this video is getting too long already. Now we have that a naught already is equal to 1 over pi the integral from minus pi. Sorry, this chalk is disturbing. Sorry about that. So we have 1 over pi the integral from minus pi to pi of f of x dx. So Fourier series for odd function, it means f of x is odd. And we have seen that for odd function, if we want to find the area, we have to integrate from 0 to pi and double the result. And the result here is minus a plus a, and this will give us 0. So it means that a naught will be equal to 0, because since f of x is odd, this is what we have, and we see that it gives us 0. So for odd functions, a naught is equal to 0. What about a sub n? A sub n is equal to 1 over pi the integral from minus pi to pi of f of x cos nx dx. Cos nx dx. And we have seen that Fourier series for odd function, f of x is odd and cos is even. Don't forget, this is the cos graph, the cosine graph. Cos is an even function, so this is even. And we have seen that odd function times even function will give us odd. So it means this function is odd, and if this function is odd, we integrate from 0 to pi a minus a to give us 0. So this means that a sub n is equal to 0. A sub n is equal to 0 for f of x equals odd. What about b sub n? B sub n is equal to 1 over pi the integral from minus pi to pi of f of x sine nx dx. And we said Fourier series for odd functions. It means that f of x is odd and sine nx is odd. Don't forget, sine is an odd function. From the graph, sine is an odd function. So odd times odd will give us even. Don't forget, even. So it means this function is even. And we said that for even function, we have something of this nature. We have a here, and we also have a here. We have minus pi to pi. So we can just integrate from 0 to pi and double the result, a plus a, which is 2a. So it means b sub n is equal to 2 over pi, the integral from minus pi to pi of f of x sine nx dx. So this is what we have for even and odd functions. So please take note, for even function, we only need to find a naught and a sub n, because b sub n give us 0. And for odd function, we only need to find b sub n, because a naught and a sub n will give us 0. So in case you are given any Fourier series to expand, if the function is even, just find only a naught and a sub n. Don't find b sub n, because it will give you 0. But if the function is odd, don't find a naught and a sub n. Just find only b sub n, because a naught and a sub n will give you 0. So this is what we have. So let's look the next video for intensive solving of Fourier series question. So please, if you are new to this channel, do well to like, share, and subscribe. See you in the next video. Thank you.